You can see from the highlighted points here that we're going to have a look now at the hydrogen emission spectrum, and that's explained by Bohr's model of the atom. Now, hopefully you can recall that with Rutherford's model, there was a flaw in that it wasn't able to explain the fact that the hydrogen emission spectrum was quantized. And with the Rutherford model, it was suggested that energy should be radiated across all wavelengths, but we see from hydrogen that there are only specific wavelengths that are produced. So we're going to have a look at that aspect in more detail, and we're going to start first of all by identifying that when we're considering the orbits, each orbit is associated with a particular energy. So the orbits of Bohr's model have a specific energy, and we can calculate what those energies are. And there's a fairly simple equation. It's not one that's in the data booklet, but it's important to be able to identify how it relates to the next diagram that we're going to have a look at. So the equation here is En is equal to E1 over n squared. So that value of E1, we need to know what that is, and that's going to be equal to negative 13.6 electron volts. So note I'm dealing in electron volts here. It's just a little bit easier to write these energies in electron volts than it is to write in joules. So that E1 is the energy of the first energy level. Note that it's a negative for two reasons. One is that when we have a negative energy, it means that energy needs to be supplied. So the negative 13.6 electron volts indicates that we would have to supply 13.6 electron volts of energy to get the electron to a zero energy state. And that means that we're stripping the electron from the atom, so the atom will be ionized. Secondly, if we dealt with the energy level being zero and worked our way up, we can't really use this equation En is equal to E1 on n squared. Now we could go through and do the calculations for all of those values of En, and if we did, we'd find that we have a list of energy levels, and so rather than just listing them out, we're going to represent them in an energy level diagram. And I'm just going to paste that under here, and then we'll talk a little bit more about it. Now, oftentimes with diagrams that I use, they aren't drawn to scale. This one is drawn to scale, and we'll have a look at some of the aspects of it. On the left-hand side, we have the energy level, and the energy level is the same as the orbit. So n equals 1 is the ground state. So that if you ever see that term in the ground state, that means that n is equal to 1. We then have n is equal to 2, 3, 4, and 5, and you'll notice that those energy levels get closer together the higher we go. Notice the top one is that n is equal to infinity. So that means between 5 and n is equal to infinity, we have an infinite number of energy levels, so they just keep getting closer and closer and closer together. We usually will only draw up to about 5 or 6 on an energy level diagram. After that, the differences between them are quite small and not really worth representing. On the right hand side, we have the energy in electron volts. You can see again down the bottom, negative 13.6 electron volts when n is equal to 1. You could substitute in the values for n being equal to 2, 3, 4, and 5 to calculate those values there, just to confirm that they are the correct values. Now, we mentioned in the previous video that photons are emitted when an electron falls from a higher to a lower energy level. And we're going to have a look at that scenario in a bit more detail. And we'll use a specific example, that being for the first one, really. So, for example, let's deal with falling from n equals 2 to n equals 1. Now, when I say falling, what I mean is that we're going to start with an electron positioned at this energy level here, and then it's going to drop down to this energy level here, and in the process it's going to release a photon which has a certain amount of energy and a certain wavelength that we can calculate using E equals HF, and then also E equals HC on lambda. Now, in this scenario, I'm drawing that arrow from n equals 2 down to n equals 1, but the electron doesn't actually exist in that space. It is either at n equals 2 or at n equals 1. So there's no physical movement between the two energy levels. Now, if we look at the amount of energy that's being radiated off, we'd have to look at that change in energy. And for this calculation, we're just going to look at the higher energy level minus the lower energy level. We can figure out what that's equal to by substituting in negative 3.40 minus negative 13.60. We end up with a value of 10.20 electron volts. Now, because we're going to be calculating the wavelength of the light here, we need to convert that back to joules. So we'd have to multiply that value by 1.60 by 10 to the negative 19, and that gives us a value of 1.63 by 10 to the negative 18 joules. So there's the first important step. We now have the energy that's associated with that photon, so that's this quantity here, and we can use that to calculate the frequency of the photon. And that's the equation that we just jotted down before, and we can rearrange that to calculate the photon frequency. So delta E is equal to HF, so F is equal to delta E divided by H, so that's a value of 1.63 by 10 to the negative 18 divided by our value for Planck's constant, 6.626 by 10 to the negative 34, and so the frequency there is 2.46 by 10 to the 15 Hertz. Now, usually when we're dealing with photons, it's the wavelength that we're a little bit more interested in, and so to calculate the wavelength, we can use the wave equation. So C is equal to F lambda, and so we know then that lambda is equal to C over F, speed of light being 3 by 10 to the 8, frequency as we just calculated was 2.46 by 10 to the 15, and that gives us an answer of 1.21 by 10 to the negative 7 meters, which we can write as 121 nanometers. So that's 121 by 10 to the negative 9. And that would be in the UV range. So it would be a UV ray. So there's the calculations that we can go through to determine how much energy is released when an electron falls from a higher energy level to a lower energy level. In class we'll go through and calculate a few other energies and the associated wavelengths to start to have a look at how it is that specific wavelengths of light are produced from a hydrogen atom. It's also important to note here that this process can be generalized by considering all the steps that we've gone through to calculate that value for the wavelength of light. And this equation was actually discovered prior to Bohr's model of the atom being determined. And so to go through those steps, we can derive another equation that will make it a little bit quicker and easier to calculate what those wavelengths are. So the first step that we went through was to calculate that change in energy, moving from a higher energy level to a lower energy level. To generalize that, we're always going to start with the higher, so the initial energy level, minus the level that it falls to. In the example, it was from 2 to 1, could be from 4 to 3 or 3 to 1, but we're always going from the higher to the lower. If we think about those energy levels though, that is given by the equation E1 over Ni squared, and EF would be given by E1 over Nf squared. That's using the equation for the energy level for each value of n. We can then factorize and take E1 out the front, and we're left with 1 on Ni squared minus 1 on Nf squared. So there's the first step. The second step was that we took that value of delta E in order to calculate the frequency of the photon. So from there we had that F was equal to delta E over H. Now that expression for delta E we can substitute in here, and so we can write E1 outside of 1 on Ni squared minus 1 on Nf squared. I should also mention here that this derivation is not an important one for you to be able to reproduce. It's just one that's useful to see how the equations are linked. From there we went to the wave equation, C is equal to F lambda, and we calculated lambda by taking C divided by F. So if we substitute in here, we get a very long and messy equation, C over E1 outside of 1 on Ni squared minus 1 on Nf squared, all divided by H. Now if we simplify that a little, we can, if we're dividing by a fraction, we can multiply by the inverse. So we can then write that E is equal to Hc over E1 outside the bracket. So Ni squared minus 1 on Nf squared. And at this stage we're going to just find the inverse. Because we've got this fraction with fractions in it still, we're going to flip that and turn it into 1 on lambda is equal to E1 on Hc. So I'm going to also factorise those terms out the front, and then we're left with 1 on Ni squared minus 1 on Nf squared. Hopefully you can identify that this term that we have out the front is made up of constants. So E1 being the energy of the first energy level, H being Planck's constant, and C being the speed of light. So if we substitute in, we find that 1 on lambda is equal to negative 13.6 electron volts. Multiply that by the conversion factor of 1.60 by 10 to the negative 19 to get that in joules. Divide that by Planck's constant, 6.626 by 10 to the negative 34, and multiply that by the speed of light, 3.0 by 10 to the 8. And those general terms, 1 on Ni squared minus 1 on Nf squared. Almost there. 1 on lambda is then equal to, I'm going to get rid of this negative here by taking it inside the brackets. So we'll write that the number out the front is 1.097 by 10 to the 7. And if we multiply that negative inside, that is going to flip that term around. So it's now 1 on Nf squared minus 1 on Ni squared. And we're going to then take that number, 1.097 by 10 to the 7, and write it as a constant term. That constant is going to be the letter R, and that's going to be multiplied by 1 on Nf squared minus 1 on Ni squared. And that's the equation that we can use to make the process a little bit quicker. So notice now all we need to know is the final energy state, so the lower energy state, the initial energy state, and then we can calculate what the wavelength is using this equation. So just to notate that, as we know, lambda is the wavelength in meters. That's the wavelength of the photon. The value of R is known as Rydberg's constant. So that's named after the person who discovered this relationship and how it applied to the hydrogen atom. Note that it is specific to hydrogen, given that we used E1 for hydrogen, and that value of R, as we saw in the equation above, is 1.097 by 10 to the 7, and the units are per meter. That is given in the data booklet, so that's a constant that you don't need to memorize. It's one that you can look up. Note that for other elements, they would have different values for R, so we can only use this value for hydrogen. And as I mentioned, Ni is the higher energy level, and Nf is the lower energy level. So as I said, we'll go through and apply this calculation to other energy levels for hydrogen, and we'll identify the wavelengths of light that are in the visible spectrum, which are specific to hydrogen.